Okay, so welcome everyone to our monthly quantitative finance seminar series here at the Fields Institute. Before we get started, just a little bit of housekeeping. I'd like to remind you that if you would like to ask a question, please type it into the chat. And if it's pertinent, I'll interrupt the speaker in the middle here because that's his preference. And you can ask the question yourself. And at the end, we'll also have some more discussions and we won't try to keep Peter too late because he's zooming in all the way from Turin in Italy. And but normally we'll have some casual discussions afterwards, but we'll try to keep that one short today. So before introducing the speaker, I'd like to say thanks to Scotiabank through the Center of Financial Industries for continual support of the seminar series. And now I'll introduce our speaker. So Peter Tankov is a professor of quantitative finance at ENSAE, the French National School of Statistics and Economic Administration, now part of the Institut Polytechnique de Paris. And he earned his doctorate from École Polytechnique under the supervision of Ramakant, was previously a professor at the University of Paris, I never pronounce this right, Diderot, and a lecturer at École Polytechnique. His research focuses on applied probability, quantitative finance, energy finance, and green finance. His works on topics related to climate-induced financial risk, electricity markets, energy mix scenarios, forecasting and risk management for renewable energy industry. He's the author of more than 45 research papers and a reference book on stochastic modeling with jumps. So with that, Peter is going to tell us today about optimal exploration of an exhaustible resource with stochastic drivers. Peter, the floor is all yours.
Yes, thank you very much. So this is a joint work with my co-authors, Ivar Ekland, Wolfram Schlenker, Brian Wright. Ivar is in Paris, Wolfram is in Columbia, and Brian is in Berkeley. And so the title is The End is Near, and we are talking about the end of oil, not the end of the world. And I was also joking that we've been working on this paper for at least 2.5 years, I guess, since before COVID. And now I hope that the end is near. All right. So this is an old problem in economics, in the economics of exhaustible resources. And it actually goes back to the famous cake eating problem by Hotelling, the famous paper Hotelling 31, the economics of exhaustible resources, where there is a single infinite-lived consumer who discounts future utilities at a constant rate, and there is a quantity, initial quantity R of a non-renewable good that we shall call reserves in this paper. And so the consumer wants to optimize the schedule of consuming this reserve. So CT is the rate of consumption, and we want to maximize the value of this amount R, which is defined as the maximum over all consumption strategies of the integral of discounted utility of this consumption rate. And of course, under the condition that C is the derivative of R of T, right? R is the level of reserves, C is the rate of consumption, and R must always remain positive. Well, this is the classical Hotelling problem. And so this defines the value function, and from the value function, by differentiating, if you assume that the utility is measured in monetary units, you may define the so-called shadow price of this resource that we will spend a lot of time in this talk discussing. So this is just the derivative of our price at time t is the derivative of this value applied to the reserve level at time t. So this is the Hotelling problem, and it is very easy to solve using, for example, Lagrange multipliers, and also very easy to show that the price in this Hotelling problem is simply a constant times the exponential RT. So the price grows with the rate of interest in the Hotelling model. And so Hotelling writes that it is a matter of indifference. Hello, Brian.
Hello.
It's a matter of indifference to the owner whether he receives for a unit of his product price P0 now or P0 times exponential RT after time t. All right, so this is the Hotelling solution. And now the question that we want to ask is how, in what sense should we expect this rule to hold when there is in addition to this known reserve level R, there is also some randomly hidden deposits which one can explore at a cost, right? So for example, in this graph, we see that in red, this is the proven reserves of oil, which are actually growing very fast for the last 70 years, right? So clearly for oil, the assumption that there is a constant and known level of reserves is not suitable, right? So we need to take into account exploration. And so we work on the now almost classical model by Arrow and Chang, which is defined as follows. So they assume that the agent, in addition to this reserve level R, has access to some amount of land that can be explored. So this amount is denoted by X. So X is the amount of unexplored land, and it is modeled as a one-dimensional interval, right? So this is the interval. So this is the land that we want to explore. And on this land, there are at some unknown random locations, these deposits of oil or some other mineral that we model. So the stars are other deposits. And we assume in Arrow and Chang model, they assume that these deposits are distributed according to a Poisson random measure. So psi k are the jump locations of a Poisson process with intensity lambda. And then we explore this interval from left to right. And the cost for exploring an interval of size delta is k times delta. So the cost of exploring a given amount of land is proportional to the amount of land that we want to explore. And once we have done the exploration, there is no cost for extracting already explored reserves for consumption. So we pay only for exploration. So this is Arrow and Chang model. And many people have worked on this model. This is a well-known paper. So what did Arrow and Chang do? They studied this problem using stochastic control, derived with some kind of common sense heuristic arguments, the Hamilton-Jacobi-Bellman equation, assuming that the exploration rate is bounded, that one explores it with a bounded rate. And then they argued that at the optimal solution, actually the rate becomes unbounded, and the exploration happens in zero time at infinite rate. And there is actually an exploration frontier, so a level of reserves such that if your reserves drop below this level, this is when you start exploring. So they gave a lot of intuitions about this problem, but without, of course, proving much. And this is more or less the case for all the papers that I will mention. So these are economic papers which mostly give intuitive arguments, and our contribution would be to give rigorous proofs for these arguments. Now, a nice paper by Dersko and Sethi, which followed the Arrow and Chang a year later. And so they recognize that it is actually an impulse control problem, right? That it is not good to assume that the exploration rate is bounded if on the optimal solution this rate is unbounded. And so they work directly in the setting of impulse control, provide some insights on the solution, in particular when the area remaining to explore is small. And they also discuss the this shadow price that I mentioned, and argue wrongly that when you discover something, the price always drops down. This actually is not always the case, because if there is a discovery, the price jumps, but the price jump can be both up and down. If you had to explore a very large amount of land without finding anything before finally you found something, then the price will actually jump up because you had a negative surprise. So you were expecting to find something and you didn't find anything for a long time. Now you have very little land remaining and the scarcity has increased, and so the price jumped up. And if you discover something quickly, then the price jumps down because the surprise is positive. Then another paper worthy of mention is Lasser 84, who follows more or less the same setup as Aaron Chung and Dersko and Sethi, recognizes that the price trajectory may both rise and fall upon exploration, as I explained, yet asserts that the price of reserves is expected to drop upon exploration, meaning that in expectation, the price drops, whereas we show in this paper that actually in expectation, the price will always rise at the rate of interest. Another paper by Hagan. So for finance guys here, this is the same Hagen as in Saber model. And so he has a paper on this Aaron-Chang model, which actually was published only in '94, but circulated since '81. And this paper also derives the variation inequality for the impulse control formulation, uses some singular expansion techniques to develop some and give some intuition about the solution in the small uncertainty regime. And also they claim wrongly that new discoveries always lead to a downward jump in the price. Then there was a paper by Daryl Duffy and Taksar, '86, which reviews some early contribution, and in particular, they discuss some of they do not actually solve the problem because they solve another problem. They propose a diffusion approximation, but they discuss some of the technical difficulties of the Aaron-Chang model related to defining the class of admissible strategies that I will also discuss. Then Quen, '91, extends the framework with Bayesian learning. And in the absence of learning, he actually gets a result that is different from ours because we believe that there is some error in the proofs. And finally, the last paper was by Farid and Davis. Davis is the Davis of stochastic control. And in this paper, they apply piecewise deterministic Markov processes to a version of the Aaron-Chang model, not exactly the same one on which we are working. We also with bounded exploration rate, and they derive a Hamilton-Jacobi-Bellman equation, which is slightly different from the one that I will work on. Right, so a lot of literature. Now, with all this literature, what is our contribution? Well, the main contribution, in my view, is to provide rigorous proofs for this problem. So we prove the optimality of impulse strategies within a general class of rules, which may include both impulse control strategies and continuous strategies. Whereas in earlier papers, so either they focused on strategies, only on strategies with bounded exploration rate, or only on strategies with impulses, but without proving optimality. We prove rigorously the existence of a critical frontier which separates exploration and consumption region, show that this frontier is increasing in the amount of explored area. And finally, we show that we study this price, shows that the expected price always rises continuously at the rate of interest, but the realized price trajectory may jump both up and down upon exploration, with a final jump upon a resource exhaustion, which is always an upward jump. All right, and the strategy. So first of all, in this model, it seems simple, but it has an important difficulty because in this model, information is acquired through exploration. And in other words, the information filtration depends on the strategy that you use, because when you explore, you get some information about where the deposits are. And in order to get this information, you need to explore. So in classical stochastic control problem, usual stochastic control problem, there is an exogenous information filtration to which your control is adapted. Here, the information filtration is determined by the control. So this creates a difficulty for defining this general class of strategies and for working with it. And so to go around this difficulty, we actually start by defining a class of simple strategy, so-called bang-bang strategies, where we only consume or explore. And if we explore until we find something, and then we stop. Okay, so we define a class, a rather narrow class of simplified strategies. Then we use these strategies to define the value function and prove rigorously that this value function satisfies the AGB equation. For this value function, we prove the existence of the critical frontier, show that the frontier is increasing in explored area, and then establish the regularity of the value function, right? Because it's quite explicit because we use this class of simplified strategies. And then as the last step, since we have all these results for the value function, we can prove a verification theorem, which actually shows that this class of bang-bang strategies is optimal among a very large class of all possible strategies. Right? So we use this simple class to construct the value function, then we study it, and then we prove that this class is actually optimal. All right, so let me proceed to defining these bang-bang strategies. Right, so a bang-bang consumption exploration strategy consists of two sequences. So there is an increasing sequence of random variables which determine the times when we start the exploration. So theta n is the moment when the n plus first exploration episode starts. Right, so the first exploration episode starts at theta 0, the second one at theta 1, and so on. And then once we start exploring at theta n, we explore instantaneously in 0 time. It's an impulse, and we explore until we find something or until the all explorable land is exhausted. So this is the first component of our bang-bang strategy. And the second component is a sequence of random functions where C0 is the consumption strategy before the first exploration. So it's a function of time, and it tells you how we should explore before the first, how we should consume, what is the rate of consumption before the first exploration date. Then C1 is the rate of consumption between the first and the second exploration date, and so on. So the agent starts at time equals 0 with reserve level R and unexplored area X. We call this initial data of the problem XR. And then after n exploration episodes, after n times, the amount of land that was explored is psi n, infimum between psi n and x. So psi's are the jump times of our Poisson process, and x is the total unexplored area. Right? So when we hit x, we stop. There is nothing left to explore. So the total amount of explored land is psi n infimum with x. The total number of exploration episodes is nx plus 1. So nx is the number of finds on our interval, because n is the Poisson process and x is the size of the interval, right? And so because the last episode is unsuccessful, here we have nx plus 1. We can define the consumption process. So the consumption process basically takes these CNs and glues them together in time. So C0 before the first exploration date, then C1 between the first and the second, and so on. So CT is the consumption rate as function of time. This is our simplified class of strategies. Now we need to define which strategies are admissible. What kind of strategies can we use given the information that we have? We denote by FU the sigma field generated by the process NU. So this is our Poisson process. And it was on purpose that I use U instead of T, because this is not time. This is the land, right? U is the parameter which tells us how much land we explored. This is the Poisson process of locations, not times. Geographical Poisson process, if you want, right? So this is the sigma field generated by this Poisson process of finds. And we say that a consumption exploration strategy, this bang-bang consumption exploration strategy, is admissible for initial data XR if, first of all, for each n, the random variable theta n is measurable with respect to sigma field fxn. Right? So xn is the amount of land that we explored after n episodes. And theta n is the start of n plus first episode. So theta n, the date when we start the n plus first exploration episode, must be determined by the information that we gathered after n exploration episodes. Right? Xn is the stopping time with respect to this filtration, and fxn is a sigma field. So theta n must be measurable with respect to this sigma field. And similarly, Cn, the consumption strategy, must be so it's a function of time. So it must be measured with respect to product of fxn times the Borel sigma field of as function of time of R. Right. So this basically means that theta n and Cn must be adapted with respect to the information that the agent acquires by exploring. And second condition is that the budget constraint, which is written in this way, the initial level of reserves minus what we consumed up to date T, plus the number of times that we found something, and A is the size of a single find. I forgot maybe to explain that all the finds have a fixed size of A. So one could extend with random find sizes, but to simplify the problem to the maximum possible extent, we just say that every time we find something, the resource increases by the amount A. And so this must be positive at all times. This is the set of our admissible strategies, and we call it A, calligraphic A of X and R. X and R is the initial data. All right, so admissible strategies. And then we define the value function. So the value function is defined through these bang-bang strategies. So we maximize over all the C and theta in this class of admissible strategies, the difference of two terms. So the first term is the utility, discounted utility, and the second term is the cost of exploration. And at each exploration episode, the amount of land that was explored at the end of the episode is xn plus 1, and the beginning is xn, and we discount this. This is paid at theta n, so we discount it with the exponential minus r theta n. And we want to maximize this over all strategies. This is our value function. Are there any questions so far?
There was one, but I think it's better to.
But I think it's better to leave it to the end. Yes.
Yeah.
Then, so to move on, to move on to the solution, we define the so-called exploration operator. Now, exploration operator is basically the value that you get if at a given time you start exploring. And so you see here the value that you get by exploring, you integrate with respect to this distribution of the first jump of a Poisson process. Right? If you find after exploring H, then you get the value function of X minus H and R plus A, because you have explored H. So the first variable decreases by H and the second increases by A. So this is the term that you get if you don't find anything, then you simply get this Hotelling value function of R with probability exponential minus lambda X. So this is the probability that you don't find anything on the rest of the interval. And this is the cost that you pay for exploring. Now, if we apply this to R equals 0, so the reserve level is 0, then we can find a lower bound, a convenient lower bound for this value from exploring, which is proportional to U of A minus K over lambda. So U of A is the Hotelling value of a single find, and K over lambda is basically the cost that you pay for a single find, right? And so in order for exploration at zero reserve to be profitable, because when the reserve level is 0, we don't explore, and basically we cannot solve the problem. Simply, if we don't explore, then this means that the reserve is not worth anything, and so we are simply in the Hotelling problem, right? So we need to make sure that there is a motivation to explore when the reserve level is 0. And a simple condition for this to be true is that the Hotelling value of a single find is greater than the average price we need to pay for this single find. So we will always assume that U of A is greater than K over lambda, capital U. So capital U is the Hotelling value. And the second assumption that we make is this: our little utility function, little u of C, is 1 over alpha times C to the power alpha. So it's power utility. These are the two assumptions that we have. So basically, the cost must be low enough for exploration to make sense, and we use power utility. So the next step to simplify this problem is to write down the dynamic programming principle, prove the dynamic programming principle. Now, the dynamic programming principle, this is how it works in this problem. The value function is given by the supremum over all deterministic functions C and constants θ1. So why deterministic functions and constants? Because before the first exploration episode, you do not have any information. So the timing of the first exploration episode must necessarily be a deterministic constant, because you don't have any information yet. You don't know anything about the finds. So you simply choose a constant when you start exploring. And also the strategy, C is the strategy before the first exploration episode. So this strategy will also be deterministic because you don't have any information. And the dynamic programming principle basically reduces the program to what happens before the first exploration episode. So we need to maximize the utility of consumption before the first exploration episode. And then we have this exploration operator, which is applied to X and to reserve level after we have consumed between 0 and theta 1. Right? So now the problem becomes deterministic. So this can be proven. The proof is rather classical. We introduce the value function with n exploration dates. By background induction, we prove the dynamic programming principle for this Vn, where we would have m applied to Vn minus 1. And then we pass to the limit to prove the dynamic programming principle for V. So this presents no specific particular difficulty. So first step, dynamic programming. Then using this dynamic programming principle, we characterize the value function. So this actually involves several steps. First of all, we obtain some kind of weak AGB equation, and then from this weak AGB equation, we prove one by one different properties of the value function, which are not so trivial. So the value function is concave in R, continuously differentiable in R across the exploration frontier. So there is smooth fit. Sorry for this bracket, it should not be there. And it is the solution of the following Hamilton-Jacobi-Bellman equation, or inequality, if you wish. So the maximum of the two expressions is 0, where this expression corresponds to the consumption region. This is basically the equation that you have in Hotelling problem, ordinary differential equation. And this is the exploration region. So in the exploration region, the value is equal to the value obtained from immediate exploration. This is the exploration operator. And the terminal condition, when there is no more land to explore, then V is equal to the Hotelling value of R. All right. So from this equation, we can define the consumption region where V is strictly greater than MV. So it is not optimal to explore immediately, and the exploration region where V is equal to MV. So this is the region where it is optimal to explore immediately. This is our first characterization. Second result, we characterize this exploration frontier. So the frontier between the two regions. It turns out that for every X, and this is already a non-trivial result because you don't have this in all stochastic control problems, it may turn out that actually there are many regions that the region is not connected, for example. But here in this problem, we have been able to show that for every X, there exists R star of X, a function R star of X, such that the consumption region contains all couples X and R with R strictly greater than R star of X, and the exploration region is the all couples XR with R less or equal than R star of X. Moreover, this function, the exploration frontier, is decreasing. So this means that it is decreasing in X, meaning that X is the unexplored area. So when you explore, X decreases and the frontier goes up. And it is also continuously differentiable on its entire domain. All right. So this is what I more or less already explained. There is a critical reserve frontier, a smooth function R star of X such that it is optimal to explore when and only when the reserves are below R star of X. And this frontier is decreasing in unexplored area or increasing in explored area. In other words, as the resources become scarcer, it becomes beneficial to explore early. So as the level of unexplored resources drops, you start to exploring with a higher and higher level of reserves. because the reason for this is that when you still have a lot of resources in the land, you don't really care that much about scarcity, right? And so there is no particular reason for you to explore very early. You know that there is a lot of them left. However, when you know that when there is little left in the land, then knowledge of how much exactly is left is important to optimize your consumption. So then you have you are incentivized to explore early, meaning that is with a higher level of reserves. I will come back to this when we discuss numerical simulations. So this is the strategy for proving the main results. I will not go into details of the proofs. So first, from dynamic programming principle, we deduce some kind of a weak form of AGB equation, which nevertheless allows to define consumption and exploration regions. Then from convexity arguments, we show that there is an exploration frontier. We prove that smooth fit principle holds at this frontier, and this shows the regularity of the value function. And then we employ a geometric argument to prove that the exploration frontier is decreasing in the unexplored area X. All right, so this is our weak dynamic programming equation. So this can be deduced directly from dynamic programming principle. All right, so from dynamic programming principle, we can deduce that V is the solution of this AGB equation in the following sense. So first of all, V is always greater or equal than MV. Then for all X and R, we have that U star of this weak derivative of V is less or equal than RV. And then at all points where V is strictly greater than MV, V is differentiable and satisfies this equation in the usual sense, right? So this is this does not say we cannot deduce from dynamic programming principle that V is differentiable or smooth, but we can deduce a number of properties which nevertheless allow to define the consumption and exploration region and continue to work. Now, the third result that we have is the characterization of the optimal bang-bang strategy. Now, to explain the characterization of this strategy, it is probably better, rather than looking at the formulas, which are not easy to understand, it is better to look at the graphs, right? So in these graphs, although the variable X in this problem is, in our Chang model, is the unexplored area, so X is how much land remains to be explored. Here, we plot the graphs as function of explored area, because it seems natural to explore from left to right, right? So we explore in this direction. We start with unexplored area of 1, and as the exploration proceeds from left to right, so the explored area increases from 0 to 1, and the unexplored area decreases from 1 to 0, right? And the yellow line is our critical exploration frontier in the plane Rx. So it increases as we explore, and it is decreasing in the unexplored area. And here is the strategy. We start at the point A. At the point A, we are above the frontier. This means that we start consuming. There is no exploration. So the reserves, the variable R decreases and the variable X stays constant. We go down. We go down until we hit the frontier. When we hit the frontier, and this happens in finite time, when we hit the frontier, we start exploring. So when we explore, this happens in 0 time. This is instantaneous. And during this period, we do not consume. So R remains constant and X decreases. So we explore, the unexplored area decreases. Then we explore until we find something. So when we find something, the reserve level jumps up. And here, two things can happen. Either we are above the frontier, or we can also be below the frontier. Right? Here we are above. So then we stop exploring and we start consuming from our reserves until we hit the frontier again. When we hit it, we start exploring again. We find something, we jump up, we are again above the frontier, and then we start consuming until we hit the frontier again. And now, at this time, we start exploring, but for a very long time, we do not find anything because it's random, there are no deposits. And when we finally, at this point F, find a deposit, it turns out that we explored so much land that when the reserve level jumps up, we are still below the frontier. So here we do not consume, we start exploring again, we find something, there is another find, and it is after this second find that we start consuming. And then when we hit the frontier again, we explore, but here we don't find anything. So all the land is exhausted. And the right graph illustrates the different variables in our model. So the explored area in black, the reserves in brown, the price in green, and in red, this is the rate of consumption. And here it is interesting to see what happens to the price, for example. The area we have seen, this is just the area to explore, but the price, the first two finds correspond to a downward jump of the price because we found something rather quickly, so the price jumps down. But the third find here, the third find corresponds to a very large area to explore from F to H because the area goes up to 1. So we explored almost the entire interval. And so the surprise is negative. We didn't find anything for a long time, and the price here goes up. And then there is one last upward jump of the price right here, which happens at the exhaustion. And then the price grows with the exponential throttling rate. All right, so this is our characterization of the strategy, and probably there is no point in trying to explain the formulas. It's much clearer with the graphs. All right, now the last result, or maybe the one before last, is, as I promised, the proof of optimality of these bang-bang strategies among a general class of strategies. First of all, I need to define the general admissible strategies. I will say that now a couple of processes, C and X, is a general admissible strategy for initial value little x and r. So C is the consumption process and X is the exploration process. C takes values in R plus, it's consumption rate, and X is increasing an increasing process. So this simply tells you as function of time how much you explore, and satisfies, it starts from 0, xt is always less or equal to x. And now this is the measurability condition. The measurability is formulated in terms of the inverse mapping of x. So since x is an increasing process, you can define a generalized inverse, x minus 1 of u, which is the first time when x of t becomes greater than u. And so the condition for admissibility is that this process x minus 1, so the inverse mapping of x, must be adapted to the filtration of the Poisson process. In other words, so the inverse mapping of u is not, so x tells you how much you need to explore up to time t, and the inverse mapping tells you when you explored, at what time do you explore a given amount of land. And this process must be adapted to the filtration of our Poisson process, which determines where the resources are. So it is more natural here to work with this inverse mapping to define this measurability condition in a natural way. Then there is the budget constraint. And then we show that for any such, so sorry, the word continuous should not be here. It's not continuous, right? X doesn't have to be continuous. It can jump. This is actually the most general strategy, which can include both continuous episodes and jumps. So let Cx be an admissible strategy of this form. Then the value of this strategy, and the value is defined as the discounted utility minus k times the cost of exploration, and the cost of exploration is simply the integral of this discount factor with respect to this increase in process x. And so this value is always less than v of xr, where v is our value function defined with the bang-bang strategies. And so this shows that since we characterize explicitly the bang-bang strategy, this shows that the bang-bang strategy is optimal, because for any strategy from this general class, you cannot get a higher value. All right, and I guess the last element of discussion is the behavior of prices. As in the hoteling model, we can define the price from the marginal utility, from marginal value function, sorry. So the price process PT is the derivative of V with respect to R, evaluated at the point RT, where RT is the reserve level at time t, and little x minus xt is the amount of unexplored land at time t, because little x is the initial amount of unexplored land, and xt is the exploration process between 0 and t. And now we show that the price process is continuous within the consumption region. So within the consumption region, when we consume, the price simply grows at the hoteling rate. And then when RT hits the frontier, the price jumps. The jump, as I mentioned already, may be both positive and negative. In case of successful discovery, it will be positive if we had to explore a very large area, and negative if the area to explore was small. At the end, there is always a positive jump. When all the resources are exhausted, the jump is always positive. And moreover, we can show that PT, the discounted price in this model, is a martingale. And in particular, so in expectation, the price satisfies the hoteling rule. The expected price grows with the rate of interest. So these are the principal findings that we have. And now a few numerical simulations. As I mentioned, we plot everything is plotted as function of explored area, which corresponds to 1 minus x, because it's more natural we explore from left to right. Now, this graph simply shows the consumption and exploration region, right? So this is the frontier, which is increasing. Maybe it's not so interesting. Once again, okay, let me skip this. This graph shows the trajectories, which I also already discussed. And maybe the most interesting. So let me maybe come back to the parameters. So we'll present 3 sets of parameters. The first parameter set has very low intensity of discoveries. So 2 finds per interval, high exploration cost, and a large discovery size. So this is a single trajectory. You see there are small number of discoveries. And this graph shows the average over 1,000 simulations. So this is maybe the interesting graph that we want to discuss. Now here, we show the price. And these shaded areas give an idea of the distribution of prices. The black line, which is hidden behind the red one, is the average. And the red line is the interest rate, simply grows with the interest rate. So this shows that the average price does indeed grow with the interest rate. And another interesting curve is the purple one. The purple one is the average, which is taken only over the trajectories which have not reached exhaustion, on which the explored land has not been exhausted yet. And we see that this curve grows at a much slower rate than the rate of interest. And this shows why many papers which tested the hoteling rule did not actually find that the prices grow with the rate of interest. This is because when we test it, well, there is no mineral for the moment for which has been exhausted. So we are always on this trajectory, which basically conditions on no exhaustion, and the hoteling rule doesn't hold. Now, these graphs show the same situation, but for a higher intensity of discoveries and lower cost. Now here we see that the frontier is no longer linear. Now, in the beginning, we see that the critical reserve level is very low. So when we start, we do not explore until the reserves drop at a very low level, because we know that still there is almost an unlimited amount hidden in the land. So there is no point. The information that we gain from exploring is not very important. So we prefer to wait in order for the discount factor to play and to save some money. All right. Critical price, critical reserve level, single trajectory. And here also average interest rate and average given no exhaustion. And we see that once again, the price grows, average price grows with the interest rate, but the average price given no exhaustion grows at a much slower rate here. It is also growing, but at a much slower rate than the interest rate of hoteling. And the last example, we took a very high intensity of discovery, so 40 mines on average in the interval, low discovery size, and low exploration cost. And here we observe some interesting phenomenon that we were not able to explain theoretically. There is basically something like a break point in the frontier, right? Actually, theoretically, we can show that the frontier is always positive, but here it is like exponentially small. So numerically, it is undistinguishable from zero. And then at some point, the frontier becomes almost linear and starts growing. So there is a point on the interval such that to the left of this point, the frontier is almost zero. So we do not explore until we consume all the available resource completely. And then at some point, this frontier starts going up. So the scarcity comes into play. Here, there is no scarcity. And from 0.2 onwards, the resource become scarce. We start to feel scarcity. And so we start to explore early. And here, once again, these are the average price and the average given no exhaustion. We see once again that it grows at a slower rate than in the beginning. None of the trajectories attain exhaustion, so the two curves almost coincide. But then, as some of the trajectories start to exhaust, the average given no exhaustion starts to grow at a much slower rate than the average price. All right. So to conclude, what do we learn from this model? So in this model, if the reserves are large when we start exploring, this is a sign of scarcity, right? Like in the graphs here, for example, if we start exploring when the reserve level is still large, then this means that the end is relatively closer than when we start exploring, when we do not start exploring until reserves get very small, right? So increasing reserves in this model is a sign of scarcity. The high prices also imply that the end is nearer. A positive jump in reserves, which is accompanied by a negative jump in price, implies that there is scarcity is low, the end is farther away. And if we have a positive jump in reserves, which is accompanied by a positive jump in price, this means that we had a very long unproductive, very long geographically. I mean, we had to explore a very large amount of land. And this means that the end is nearer than before, right? We explored a lot, so there is not so much remaining. So this may be a sign of scarcity. And if the end is already near enough, then we will necessarily see a positive jump. It can be shown that we will necessarily see a positive jump in the price prior to resource exhaustion. So a positive jump in the price is not necessarily a signal of a resource exhaustion. It may appear even when there is still a certain amount of resource left. And I think this is my talk. Thank you.
Great, thank you, Peter. And I guess we can open the floor now for some questions and discussions. I'll remind you that if you do have a question, you can type it in the chat, or in fact, given that we're a smaller group, we can also just unmute and ask the question. I see Louis Belisle had a question earlier on, and maybe now is a great time to ask it.
Thank you, Sebastian. Yeah, my question is very, very simple. Like you mentioned that other papers have said that it is wrong to assume that there's always a negative jump in price when there's new discoveries. So do we have like empirical evidence of that happening, that like sometimes there's an increase in price? And I guess that leads me to the second question. I came a bit further along, like I think I saw that the exploration frontier is not dependent on the price, or isn't necessarily like the exploration frontier will influence the price. Whereas I would have imagined that it may have been the causality may have been the other way around, that as the price increases, it increases incentives to explore.
No, here there is a one-to-one correspondence between reserves and price, and the exploration frontier, you can either write it in terms of price, so you explore when the price is sufficiently high, or in terms of reserves. There is a one-to-one mapping. Right, and concerning the empirical evidence, I mean, I don't know. I haven't really looked at this type of data, and I agree that this would be very interesting from an empirical point of view. Whether maybe not for oil, but whether for some type of minerals, you could really observe that upon finding something, there is an increase in the price. I mean, maybe this could happen if, in order to find something, you really had to change the technology. You realize that you find a deposit, but you realize that in order to find it, the cost of extracting these kind of deposits would be very high.
Thank you.
Other questions from the audience? Okay, I had a couple, Peter. One thing I was curious about is, I know that there's this work that Ronnie Surkar and Mike Lukowski, they've done some work on this exploration and exhaustibility I think it's a game setting there, right? Where they have a producer who can explore to replenish their reserves, but then there's also a green energy provider. But I think there's a first part where there's just the producer. And do you know of the work, and do you know what the similarities and differences are here? Because I just vaguely remember it, but
yeah, so I also vaguely remember. So this is not the same model, of course. And yes, thank you. I will need to look in detail at this paper, but I don't think I can discuss it now because yeah.
Yeah. Okay. Great. I do have some other questions, but I do see that there's a hand up here, and you can go ahead and unmute yourself. And ask away.
This is Brian Wright, just
Brian. Yeah.
Making one comment about the question about what happens when you have a big discovery. Actually, there are lots of things going on when people make big discoveries. There is an unpublished paper from Germany about this, and it seems like the evidence is sometimes the price goes up and sometimes it goes down, but we can't be sure it's being driven just by the factors that we see in this model.
Okay, cool. Thanks for the comment, Brian. Are there any other questions from audience? Because if not, I have a few more that I'd love to pick your brain on. So one thing I was curious about is whether the memory list property, I think, helps with your setup for writing down the DPP, and then also showing, I think, that the bang controls are optimal. Have you thought about what happens if your process for where discoveries happen had some sort of self-exciting nature to it, or was stochastic? It had a stochastic intensity, such as like a shot noise process or a Hawk's process.
Yes.
Anything like this? Yeah.
Why would the discovery process be self-exciting? I don't know.
Well, I would imagine that sometimes you have clustering of reserves, right? that if you found something here, then it's probably likely that you're going to find something nearby due to geological factors, right? If it's oil exploration, for example, that's a thought in my mind. Again, I'm not an expert in this at all, but that was something that was occurring to me.
Yes, this is interesting. Yeah. So one extension that I know of is an extension when you don't know the intensity, and while you explore, you are also trying to learn the intensity. Here, you suppose that the intensity is known, but you can do Bayesian learning. Of course, this problem will be more complicated, but maybe something can still be done.
Okay, cool. Maybe can I ask one more then, since I don't see any coming into the audience or hands raised here. So one other thing I was curious is, you have this sort of one-dimensional exploration regime or space, whatever you want to call it. Now, I'd imagine that of course, if we're thinking of exploration in real space, then you have some sort of 2D map, and you can have a Poisson random measure that gives you locations of reserves. Maybe there has to be some finite size to them, otherwise you just have point locations. But has there been any thoughts or discussions around extending it to the context of exploring in a two-dimensional space of sorts?
Then you need to decide which ones you explore first, right?
Well, I guess you'd have to decide on how you're going to explore the space in some manner. It's almost like robot control, right? Trying to
you can draw a curve basically on the space which covers it in more or less exhaustive way, and then explore along this curve. And then this curve would be one-dimensional. But you need to decide how you draw the curve.
Okay, that's how you might get around it, or project.
Of course, learning would also be very important and more interesting in this two-dimensional setting, because while you learn much more than just the intensity of a Poisson process, you learn something about this distribution, and you can direct the exploration.
That's right.
Of course, the problem will become much more realistic, but it's probably will not be solvable.
That's what you can work on for the next 4 years. So, Louis, I see you have a question.
Yes, just I'm basically a bit on that topic of like exploration. I'm thinking in the real world, exploration and exploitation basically happen in parallel, right? So how would you take that going from the bang strategy to more of a join process? What would be the leap needed to do that, right? Having, let's say, one firm that does the extraction, sells it to the producers, and another firm that does the exploration kind of continuously, as opposed to a one-shot bang strategy.
Yes, so actually in Arrow and Chang paper, they say that the fact that in the model, the exploration is instantaneous and does not happen simultaneously with consumption is a drawback of the model, because it makes the model less realistic. So in this sense, you're right. In practice, one explores and consumes simultaneously, but I guess.
So tractability is the advantage of the bang.
This is mostly for tractability. Exactly.
Okay. Which makes sense.
Okay. Maybe Peter, I'm going to ask you one more before I let you go. Go to slide 25. There was something interesting about those heat map-like plots, in particular. There. So there are these kind of regular drops that are happening every so often, like at time 15 or 12 or so, and then time 30, and so on. What is causing that? Because this is a random. I mean, I thought the distribution of the reserves or are random and stochastic, right? So it seems odd that you get.
Yes, but the first time is deterministic. So this deterministic drop is because the first exploration, this is the first exploration date. And the first exploration date does not depend on randomness, it's deterministic.
But then why the subsequent ones?
Subsequent ones are not really deterministic. they have some stochastic nature. This is why this is not does not go straight up. But presumably, they depend on the location of the first Feynman, maybe not as strongly. And so you more or less explore at the same time, plus or minus a couple of years, right?
Okay. Okay, very interesting. Okay, well, if there are no further questions, I don't see anything coming into the chat. I'd like to thank Peter once again for a very interesting talk, and especially thanks for doing it so late. I know it's after midnight now for you, and we very much appreciate your coming in. Thanks, Peter.
You're most welcome. Maybe I wanted just to add something, one last comment about this simultaneous consumption and exploration. Actually, this is a feature of the model which appears because the frontier is increasing. If the frontier was decreasing, so imagine that it goes this way, then you can go down on the frontier and consume at the same time, even in this very, very simple model. So if you take, we have shown that the frontier is increasing for power utility, but perhaps you could find some other utility function where this property would not hold, and you would, in this very same model, have simultaneous exploration and consumption.
Actually, that was one of my other questions, is the utility function crucial in coming up with this increasing result? But so
for us, yes. Well, in some of the papers, they do not say that it is a power utility and still argue that frontier is increasing, but without proof, right? But
right. They argue wrongly, as you said. Okay, wonderful. Well, thanks again, Peter, and have a lovely evening, everybody. We'll see you next month.